In this video we will see how to get the right parameters from a datasheet. My name is Ronald and I'd like to show you the parameterization of this valve we've used in a former video. Many parameters to fill in. Let's assume that we need a precise position control and select therefore a servo valve. As an example, I've chosen a Moog D631 series servo control valve. If we are looking into the datasheet, the first figure shows a cross-section of the valve. It's interesting, but doesn't help to find parameters. Next are some specifications, which are also interesting, but still not helpful for our task. On the next page, we find a very useful diagram. It allows us to choose the right size of the valve. In our case, I want to have a 40-liter valve. Not available. You have to know that the nominal flow of a valve is given either at 10 bar pressure drop or 70 bar pressure drop from P to T with a shortcut between A and B. So this curve belongs to my valve. It has a nominal flow of 16 liters per minute at 10 bar, respectively 40 liters per minute at 70 bar for two valve edges. Therefore 5 bar, respectively 35 bar per single valve edge. What's next? Another performance specification gives a parameter for no leakage flow. The corresponding pressure difference we can find in the footnote. All other flow parameters remain at their default values. The servo valve has a zero cut, hence a relative overlap is zero. And we have a symmetrical valve. All valve edges have the same characteristic, so the factor for flow adjustment remains at 1. The second page of the parameter dialog defines the dynamic behavior of the valve. This means the reaction of valve spool on input signals. If we turn one page in the datasheet, we find two more diagrams. One shows a step response, the other the frequency response. Let's start with the frequency response. The valve model in Activate uses a second order element as transfer function, and if you are looking at the Bode plot, it looks very similar to a plot of a second order element. Which parameters can we get from the diagram? Well, for one thing, this is a frequency. The necessary angular frequency is the frequency at -90° phase shift, in this case 50 Hz. Why I take the 25% curve we will see in the next diagram. The damping seems to be close to 1. If it were less than 1, we would have an elevation of the amplitude before it drops. We will determine the exact value later. The last diagram, the step response, helps to determine the maximum and minimum velocity of the spool. If the step is higher than 25%, we recognize a section of constant speed. This constant speed is our wanted parameter. The gradient of the curve is round about 15.5 milliseconds for 100%. Thus, the velocity is 64.51 per second. The speed limitation is responsible for reduction of the eigenfrequency of the system. Since this reduction is considered in the valve model, we have to enter the maximum eigenfrequency, and that's the reason why we took the 25% curve. Now, let's cross-check the valve parameters. With the test rig model, we will do some experiments. The test rig consists of the valve with a constant pressure source, some pressure and flow sensors, different actuations of the valve, and measurement of input signal of the valve and the spool stroke. First, we check the hydraulic parameters. We actuate the valve quasi-static with an amplitude from -100% to 100%. The pressure source is set to 70 bar relative, respectively 71 bar absolute pressure. The pressure at port A and B is 35 bar, the half of 70 bar. This is correct, since we have two identical resistors in series. The flow is proportional to the input signal. Maximum flow is at 40 liters per minute, which also is correct. If we zoom into the middle area of the flow, we recognize a deviation from linear behavior. This is caused by the parameterization of the leakage. In middle position, all metering edges are slightly opened according to leakage parameter. There's a flow from P to A, P to B, A to T, and B to T. As consequence, we have no external flow between A and B. If we disable the connection between A and B, we get another characteristic of the valve caused by the leakage. Around the middle position, the pressure in A and B changes smoothly from supply pressure to tank pressure. This effect is called valve pressure gain. In practice, the pressure gain states the valve reaction towards external disturbances aimed at changing the actuator position. After checking the hydraulic parameters, we now verify the control parameters. I replace the continuous actuation of the valve by a step function. In order to see the spool stroke at different input steps, I change the window option of the scope from reduce to overlay. Additionally, I reduce the simulation time to 0.1 second and set the initial stroke to middle position. We start with a step from 0 up to 100%. The result shows a typical limitation of speed. Next is a step up to 75%, 50%, and 25%. I think the results fit very good to the datasheet figure. The last property I want to check is the dynamic behavior given with the Bode plot. I've extended the simulation model by a signal out element for valve input and valve stroke. With these signals, we can perform an analysis after simulation. The signals have a sampling frequency of 1 kHz. As excitation of the valve, I use a variable frequency sine element which outputs a sine with amplitude 1 and a variable frequency starting at 0. Within 50 seconds, the frequency increases up to 100 Hz. The time-based results shows a reduction of amplitude with increasing frequency. That's okay, but not enough to judge the results. I perform an FFT with an OML script and represent the results in a Bode plot. The OML script is inside the exec OML script element, which allows me to run the script at any desired point of time independent of a simulation run. In the Bode plot, we get the confirmation of our parameters. At a phase shift of -90 degrees, we find the eigenfrequency of 50 Hz. Finally, a fine-tuning of the damping could be done to get even closer to the given frequency response. But note, as with all other parameters, data and graphics in datasheets may be rounded or beautified. At the end of this video, I'd like to point you to our forum. It's a great place for questions and knowledge exchange in all matters concerning Compose and Activate, but also for all other Altair tools. Thanks for watching and see you at the forum.